Hey guys, how's it going? I need to get a screen here or something to let you know what's going on. Tonight we're going to go over questions 4, 5, and 6 from the Gravitation packet. The solutions to this are already posted. There's a couple challenging questions. Over there, number 6 is kind of a big question that you got to look some stuff up for. But not anything I would ask on a quiz. Your next homework over the weekend will be, some Regents multiple choice questions that are more along the lines of what we're trying to get out of this. I'll make a video going over some of those to help you with that. So let's get into questions 4, 5, and 6, and we'll worry about the rest later. Alright, so number 4, let the Earth have a radius of RE and mass ME. Let some object have mass M on the surface of the Earth. Equate the two versions of FG and determine the equation for G at Earth's surface. Alright, so the two versions of FG are the one we already learned, right, way back when. FG, the force of gravity on some object, is mass times G, and G was, we called it gravitational field strength. Right? So gravitational field strength, that is 9.81 newtons per kilogram at Earth's surface, right? So it's only good at Earth's surface. The farther away you get from the Earth's surface, the lower that number gets, right? So G is gravitational field strength at Earth's surface. Now the other version of the force of gravity that we've learned is the force of gravitational attraction, equals big G M1 M2 over R squared, where M is the mass of one of the objects, M2 is the mass of the other object, and R is the distance between their centers. Alright, well, what the heck do these two have to do with each other? Well, if I look at a person, right, let's say we have the Earth, right, and some person standing on the Earth, well, the person is M1, the Earth is M2, which we talked a little bit about in yesterday's assignment, right? I believe that was number 3, the last one we just did. So M1 and M2 attract. The distance between them is the radius of the Earth. So that force that person experiences, force diagram of the person, FG, should be equal to this. If we say M1 is the person, M2 is the Earth, and R is the radius of the Earth, the distance between them. So let's name M1 and M2 appropriately. Let's call M1 mass of any object. We'll call it MO. And let's call M2 the mass of the Earth. Alright? So this force of gravity is representing the force acting on this object. Alright? So that's MO times G. Alright? That equation, the force of gravity on that object. I could also, and by extension, I would know that that same force is what's pulling up on the Earth from that person, which is silly because the Earth is so big it doesn't move. That's often confusing, but it doesn't move. So let's go to the right equation here. M1 is the object, okay, all right, on our surface. M2 is the Earth, so I'll make that mass of the Earth. The distance between them is the radius. I'll call that the radius of the Earth. All right. So now that represents the force of attraction which pulls on each of them. So that is also what the force pulling the object down should be. So this equation has to be equal to that equation. So big G, mass of the object, mass of the Earth, divided by radius of the Earth squared. And I gave you a hint yesterday that G was in this equation somewhere. Well, it is, because watch this. Simple cancellation. The object cancels out. And you get the gravitational field strength is big G times the mass of the Earth divided by the radius of the Earth squared. And if you go ahead and plug in those two numbers, I'll leave you for the paper solution to look at that. You can plug in the two numbers and get it. And sure enough, using the numbers that we used over in number 3, you get 9.81 newtons per kilogram. All right? So as long as you're on Earth's surface, it's that. Now, it does turn out that if you go in different places on Earth, that field strength does vary a little bit. I used to know these numbers off the top of my head, but I want to say it only varies in the 100th place here. 9.79 might be about the lowest. And it not only is affected by radius, but because it's affected by mass, if you're in a particular place in the Earth where the ground is very dense, meaning like a mountain where it's basically granite, or, you know, bedrock is close to the surface, that is actually going to cause a little bit higher gravitational field strength. And there's these really cool mapping things out there that show Earth's gravitational field relative to the Earth. In fact, I'm going to make a note right now to post a link to that. Alright, link. Let me pause this. Alright, so moving on. Oh man, I got a new whiteboard today. I fought the hordes at Walmart to get a whiteboard. A little bit better setup. Still wobbling while I erase, but we'll just have to deal with that. Man, this is a stubborn marker. Maybe I ought to try a different marker. Anyhow, alright. Walmart was sketchy this morning. I rounded the bed aisle and the guy was coughing his lung out. Another person rounded the aisle from the other end, right? The guy was in the middle, and we both just, whoop, stop, whoop, go. He was an old guy, too, so say a prayer for that guy. All right, number 5. Determine G at 1 Earth radius above the surface of the Earth. What the heck does that mean, Harmon? 1 Earth radius above the surface of the Earth? Well, this is the way the Regents loves to word this, right? So you got the Earth, and man, look. I get to draw it again for you, my awesome Earth. I'm going to get lazy here and take a little shortcut. All right, beautiful. Our Africa is attached to North America. That is Hawaii. All right, so from the center of the Earth to the surface is 1 Earth radius. All right, 1 RE. One more radius would be another Earth radius above the surface of the Earth. It could be a satellite. Looks kind of like a TIE fighter, but whatever. It's a satellite, so its orbit is 1 Earth radius above the Earth. Its total distance from the center of the Earth is 2 Earth radiuses. So, if we double the distance between the two objects, the force gets weaker. All right? The force gets weaker as we double the distance because Fg equals G m1 m2 over r squared, right? This is the distance between their centers. If I double this, well, it's squared, right? So if I double that radius and then it's squared, it actually ends up being 4r squared, right? And because it's on the bottom, if I make the bottom bigger in a fraction, the value of the fraction goes down. So Fg gets 4x weaker. Gets 4x weaker, right? If you double the radius, it's on the bottom. So again, it's this proportional reasoning that we've seen before. I gotta do something about this reflection. I got some lights coming. Maybe, I don't know. I block it off. Anyhow, Fg gets 4x weaker, all right, by doubling the radius. Again, it's proportional reason. You're making the radius bigger, and it's squared. So however much you change the radius by, whatever factor, the effect is squared. So if you tripled the radius, the force would go down by 9 times. It goes down because it's on the bottom. So if you make the number on the bottom bigger, the force goes down. If you double the mass, one mass, the force would get doubled. If you doubled both masses, if it was like 2m times 2m, mass of each object doubled, like if it was not Earth and some other planet and the satellite was double the mass, 2m and 2m, it would be 4 times stronger. So you got to play that game. The other way to do it is like I showed you with the ones, right? Like, ignore G, that's just a constant, that's not going to change. So it's like G times 1 over 1 squared, right? The new FG is G times 1 times 1 times 2 squared. I double the radius. So it ends up being, you know, this all is 1. This one ends up being 1/4. So the new FG ends up being 1/4 of the original. All right. You can take a look at the solution for that one. All right, now the final one. I decided maybe you didn't want to watch me erase the whiteboard because it's a little harder than, you know, I would like. So, number 6. Ouchie, mouchie. Determine the force of gravitational attraction between the Earth and the Sun in 2 ways. Using Newton's, part A, using Newton's law of universal gravitation. Yes, you need to look up the masses and the distance, but hopefully you did that. Mass of the Sun ends up being about 1.99 times 10 to the 30th kg. Radius between the Earth and Sun is 1.49 times 10 to the 11th meters. The mass of the Earth, we've used that already. That is 5.97 times 10 to the 24th kilograms. All right, so let's see if any of these are on the reference table. Mean distance Earth to the Sun, 1.5 times 10 to the 11th. That's good. But we don't have the mass of the Sun. So you won't be asked it on the regions unless they give it to you. They could do it that way. All right, so the force of gravitational attraction between the Earth and the Sun. I'm going to plug everything in. G, 6.67 times 10 to the negative 11th. You know what I'm going to do right over here is I'm going to write G over here so I don't have to put the units in this equation. Newtons times meters squared per kilogram squared. I don't want to write units in this equation. It's going to get super big really fast. So as long as I list all the variables with their units, I'm good to go. 1.99 times 10 to the 30th kg, and then the Earth, 5.97 times 10 to the 24th kilograms. All right, divided by the distance between them, 1.49 times 10 to the 11th meters. And I plug this all in my calculator and I get about 3.6 times 10 to the 22nd newtons. All right, basic equation, but you know, big numbers, which is a pain. All right, so that's part A there. All right, so let's record that off to the side before I erase this. So that's the force of gravitational attraction between the Sun and the Earth. Now, generally speaking, gravity is a weak force. All right. However, when you deal with things as big as planets, masses of 10 to the 30th and 10 to the 4th, then it becomes a very strong force. Simply because of the masses. And this is what makes it impossible to make gravity fields at this time, right? The big thing holding us back for space travel is being able to manipulate gravity. But we don't have a way to do that easily with, you know, there's no artificial way to produce a gravitational field. All right, we can simulate gravitational effects using acceleration, but we can't actually produce a gravitational field. So now, B, using centripetal force concepts,